Standard medical AI classifiers suffer from a severe limitation. They operate as opaque black boxes, ingesting a chest X-ray and returning a single probability score. The physician receives a number, but no rationale, logic, or visual evidence to back it up. Clinical viability requires an integrated stack of features beyond basic classification. The system must provide localization to show where it is looking, explainability to prove its logic, uncertainty quantification to flag its own doubt, and an active learning loop to process doctor corrections. This interface is the PneumoSight dashboard. It is a full-stack AI system engineered to bridge the gap between raw machine learning predictions and actionable clinical trust. The system architecture begins when a physician uploads a new X-ray. The pipeline first applies contrast enhancement and resizing, then passes the image into an efficient net B4 classifier, which serves as the core reasoning engine for identifying pneumonia. From there, the output branches. The data simultaneously routes through a YOLO object detection model for localization, Grad-CAM for explainability, and Monte Carlo dropout for uncertainty quantification. Finally, these outputs merge into a Gemini large language model to generate a clinical report. Engineering trust requires building a pipeline where every assumption made by the artificial intelligence is visually and mathematically verifiable by a human expert before any final diagnosis occurs. The classifier operates on efficient net B4. At 18 million parameters, it strikes an optimal balance for medical imaging, lightweight enough to run efficiently, yet deep enough to isolate complex pulmonary features. Looking at this pie chart from our exploratory data analysis, we identified a severe constraint in the RSNA dataset. Only 22.5% of the patient records contained actual pneumonia cases. Furthermore, the bar chart reveals a massive volume of no lung opacity or not normal cases. To prevent the model from blindly guessing normal to artificially inflate its accuracy, we engineered a weighted cross-entropy loss function. We assigned a 3.44x penalty to the model every time it missed a true pneumonia case. This forced the network to prioritize sensitivity. The baseline evaluation yielded an area under the curve of 0.8712 and an exceptionally high recall rate. This confusion matrix details exactly what that recall means clinically. Under the optimized threshold of 0.79, the model missed only 177 positive pneumonia cases out of 902. While this high recall classifier works well for broad screening, it comes at the cost of precision. The system generates false positives, requiring a secondary layer of analysis to guide the physician's attention and filter out the noise. To guide the physician's eye, the pipeline routes the NIDS through YOLO 26, a real-time object detection model trained to draw bounding boxes around specific infected areas. Training on a laptop GPU constrained the scale of our model, lowering the mean average precision. However, using the lightweight YOLO architecture achieved an inference speed of exactly 4 milliseconds per image. This grid of X-rays displays the localization results. The green boxes represent the human-labeled ground truth, while the orange boxes prove the AI successfully identifies and isolates the lung opacities on its own. Bounding boxes solve the problem of where the AI detects an anomaly, but they failed to explain why the neural network made its original classification decision. To pry open the black box, we integrated Grad-CAM++. We attached this mapping algorithm directly to the final convolutional layer of the EfficientNet model. Grad-CAM traces the decision backward. In this positive sample, red and yellow high-attention zones clustered directly over infected lung fields. Conversely, normal baseline X-rays in the grid show blue, diffuse heat maps. This lack of focus exposes false positives, showing exactly when the AI looks at irrelevant tissue. Layering YOLO bounding boxes over Grad-CAM heat maps forces the AI to show its work. The system transforms a blind statistical prediction into an auditable piece of clinical evidence. The most dangerous flaw in any neural network is its tendency to provide highly confident answers, even when the algorithm is completely guessing. We counter this using Monte Carlo dropout. During inference, we force the model to predict the X-ray 30 times, randomly turning off different neurons. If the network has truly learned the features of pneumonia, its answers will remain consistent. If it is guessing, the answers will vary wildly. We calculate the standard deviation across these 30 passes to measure the model's epistemic uncertainty. This histogram plots the data. The standard deviation, the mathematical measure of DAP, was 39% higher on images where the model made an incorrect prediction. We mapped this variance into strict categories, using 0.05 and 0.15 as exact mathematical thresholds for low, medium, and high uncertainty. In this validation grid, you can see the thresholds applied. Cyan borders represent low uncertainty, while yellow flags medium uncertainty, immediately warning the physician to scrutinize the scan closer. Monte Carlo dropout strips away the illusion of machine infallibility. It provides a statistical signal that tells the system when to defer to human judgment. Operating these models via a command line is impossible in a hospital setting. The back-end engineering requires a Flask-based front-end built with HTML and JavaScript to make the data accessible. But a communication gap remains. Large language models cannot natively read X-ray logic, and busy doctors do not have time to parse raw JSON outputs on a ward. The Flask backend acts as a translator. It automatically structures the raw classification result, the YOLO bounding box count, and the Monte Carlo uncertainty metric into a secure, highly formatted text prompt for the Gemini 1.5 Flash API. This clinical report is the resulting output. The LLM translates the raw numerical data into a professional, human-readable radiology note detailing the exact findings and recommendations in standard medical formatting. Furthermore, the interface includes a local CRM and analytics dashboard. This tracks the total patient history, visualizes diagnosis ratios, and continuously monitors the agreement rate between the AI's prediction and the doctor's final decision. Ultimately, the user interface functions as a translation engine, converting abstract machine learning metrics into actionable clinical intelligence. If AI models are not exposed to new data and corrected when they fail, their accuracy decays over time through model drift. The dashboard includes accept and reject or correct buttons. These act as a built-in data collection engine for edge cases. This patient database tracks those interactions. When a doctor rejects an AI prediction, the system logs the correction and routes the specific, difficult X-ray directly into a secure local feedback database. Because instant online learning risks model drift from erroneous inputs, we use a dedicated PyTorch fine-tuning script. It periodically reads these verified corrections and retrains the model in batches using a very low learning rate. PneumoSight demonstrates that layering explainable computer vision, LLM translation, and active learning creates a transparent copilot, a system designed to work alongside the physician's expertise rather than in isolation.